Hello everyone, in this video I explain the methodology of this paper. First of all, we had data gathering. Basically, two types of data is gathered. First type coming from interrupting the subject and asking their fatigue levels through Borg's rate. And the second one is sensors data. Then we had data preparation. Basically, the data achieved from the sensors are processed. Then we took care of the missing values. Basically, we want to have the longest window of time that data is available for all subjects. And it was like 50 data points starting from time point 1. Then we formatted data into time series to let us uh, be able to apply time series clustering over the data that we had. In first 9 time points, we haven't seen any signs of fatigue. Basically, if you see here, so first of all, 50 data points are achieved after taking care of the missing values, and in first 9 out of 50 points, as you see, the average of the Borg's value for all the patient is same. It's like we are not sure if they are subjected to any fatigue or not, and after time point 9 you see an increase in the Borg's rate, which is intuitive because over the time we expect more fatigue. So we were not sure if we do time series clustering and basically categorize this subject into two different groups. Starting from first time point, is it meaningful or not? Or maybe we should skip some time points and then do the clustering. So for this problem we said, okay, let's look at the 9 different time points from time point, and we start time series clustering from time point 1, then time point 2, 3, 4, 5 up to the 9. Basically, so there's 9 different situations, and we want to see if you look at the time series in this aspect, does it make any differences or not? Also, time series clustering has two different measure parameters. One of them is how we calculate the distance between the time series and how we find the centroid. So there is 9 different distance parameter and 9 different centroid parameters. So at the end we have 9 times 9 times 5 different scenarios. Then after developing these scenarios, we look at the data that we had. So after formatting, there's 2 types of data. One of them is sensor data, which is we had 4 different sensor data that are a standard deviation of step distance, a standard deviation of time steps, mean peak of the jerk values, mean back angle. Also, the last time series was the Borg's rate, which is again coming from interrupting the patient and asking their fatigue level. Borg's rate is a good representative of subjects' fatigue, and there's a good literature about the jerk as a good representative of the fatigues level. So we want to see in those different scenarios, basically, if we start from time point 1 and categorize our subject into 2 groups using the jerk value and mean of the peak jerk and Borg's rate, how those clusters overlap with each other. Because Borg's rate is not very productive. you need to hire someone to interrupt your subjects and ask their Borg's rate. Also, it might be distracting for them in real cases and not actually very practical. So we want to see if we look at the sensors data which comes from uh, their jerk mean, is it are they almost same or they are significantly different from each other? So also we want to compare um, those clusters with other clusters that comes from three different time series, which is a standard deviation of a step time, a standard deviation of distance step, and mean of the angle back. So after time series clustering, uh, we want to compare their overlap. Basically, if you use different data and do time series for categorizing the subject into two different groups, how those clusters overlap with each other. We know that, like intuitively, Borg's rate are a good representative for the subject's fatigue. Also, there's a good literature about peak jerk mean as a good representative of the fatigue. So we have 9 different starting time points. We want to see if we uh, cluster our data in two different groups using the jerk and Borg's rate, how they overlap with each other. So 9 different time points, start 1 to start 9, and in each starting time point scenario we had uh, 9 different distance parameters and 5 different centroid parameters. Then we look at the overlap of jerk and Borg's rate. As you see, it's start from 93% up to just 13%. So in some cases, if you pick good distance and sensor parameter, you might have end up having very high overlap between jerk and Borg's, versus in some cases you might have just 13% overlap. So, and this overlap might differ in different time points. Let's just look at the categorizing our data based on uh, starting from time point 9, and as you see in this case the highest overlap between jerk and Borg's rate are just 73%. So we sort out our results based on the overlap between jerks and Borg's rate. Then we want to see what about the other three sensors data, how they overlap with each other. Like, so uh, if we are like if Borg's and jerk means or have high overlap with each other, is it the same between step time standard deviation and Borg's rate or not? Or how about having high overlap between peak jerk mean and Borg's rate? At the same time, all of them has good overlap with the Borg's rate or not. So we picked best 5 scenarios that in those 5 scenarios jerk and Borg's rate have highest overlap. Then we look at the overlap of other clusters made by a step time, a standard deviation of time step, a standard deviation of distance, and also angle back, mean of the angle back. So if you look at here, so This figure shows the overlap of candidate variables, which is which are distance standard deviation, angle back bent mean, time standard deviation, and picture mean. So we had 9 different starting time points, and each of them I picked best 5 scenarios that had the highest overlap between Borgs and jerk. Then those, so in this, as you see here, we have a double line here. This is the, it shows the overlap of jerk and Borg's rate in each starting time point scenarios, and also so each data point here shows the average of best 5 parameters. Also, having those best 5 scenarios, I look at the average of other sensors data overlap with the Borg's rate. As you see here, the hash line and the solid line and the Borg's rate has good overlap in those best 5 scenarios versus the dot line, which is showing the distance standard deviation, has the lowest overlap. So what does it mean? Means time standard deviation, picture mean, and angle backbend mean may end up producing same results, very similar, more similar result than distance standard deviation. And this table on top of the figure shows the overlap of the average of those 5 scenarios over the time, over different starting time points. Also, this figure shows another data saying that it doesn't matter actually when do you start clustering, as you start from the first data points or the 9th data points. The results are almost similar. There's not that very significant differences, or basically there might be some differences, but it's not very drastic. So for further analysis, we start from first time point, because we are not seeing such a drastic differences if we do clustering from the first data point or from the 6th or 7th or 9th. So far we have seen if we pick good parameters, we made of having good overlap between mean of the peak jerk and Borg's rate, and also mean of the back angle and step time standard deviation has they have good overlap with the Borg's rate. In those cases, that also jerk has a good overlap with the Borg's rate too. So it seems instead of hiring someone, interrupting the subject and asking their fatigue level, we can have sensor data, and those sensor data also might be good representative of their fatigue level. So we want to see how is predictable those labels. So we use 4 different machine learning algorithm, which is support vector machine or SVM, logistic neural network, and theorem naive based, using the physical characteristics of subjects from the height, weight, gender, and other variables, and we try to predict their layers of their clusters, which are representative of their fatigue level. These four algorithms couldn't produce basically uh, uh, good performance, and so we use a stacking approach, which basically the probability of outcomes from those four algorithms came into came into a random forest algorithm as input, and so we use a stacking approach, basically considering random forests on top of those four machine learning algorithms, trying to predict the picture means cluster labels to see if how are those predictable those labels. That was it. So there's more explanation in the write-ups, but here I just wanted to give a general overview over the method. Thank you very much.